Okay, we're doing section 5.5, doing the derivative and integral of bases other than e and applications of that. Okay, so we're going to skip half-life for now. We'll get to that in another section in a little bit. Here's some inverse functions that we'll have to be using. Y is equal to a of x if and only if x is equal to log base a of y. The ones we're going to be using the most are number 2 and 3. A to the log base a of x. The log a and log of a cancel to just x. And number 3, log base a of a also cancels, and you just get x on that one as well. So we're going to want to be using that when we're trying to solve for x on these two examples on a and b. So if I'm trying to get to the x and figure out what that is, what I'm going to have to do is log base 3 of both sides, because as we could see on number 3 up above, log base 3 of 3 would cancel to 1, and we would get that x alone. So x is equal to log base 3 of 1 over 81. And thinking back to pre-calculus, how we would figure out what this is, since we can't do log base 3 in our calculator, that's to change a base formula. So we do 1 log of 181 over log of 3, and that's negative 4. On b, it's actually the opposite. We're going to exponentiate both sides to the. So 2 to the log base 2 cancels to 1, and we have x equals 2 to the negative 4th, which is 1/16. Okay, now we're going to get to the actual derivatives. These you're going to have to know. The derivative of a to the x is natural log of a times a to the x, and the same thing follows. This is just when we have an actual function in the exponent, not just x. It's natural log of a times a to the u, leaving that completely alone, and then multiply by the derivative of whatever the exponent is. Same concept here for log. The derivative is 1 over natural log of a times x, but if we have a function there, it'd be 1 over the natural log of a times that function, multiply everything by the derivative of that function. And we did not include the integral formula, so I'm going to write this on top, and that's something that you should have written down and know. The integral of a to the x dx is equal to 1 over the natural log of a times a to the x plus c. So it looks just like on this first example, the integral of 2 to the x. Our integral is going to be 1 over natural log of 2 times 2 to the x plus c. If there's a function in that exponent, you're just going to have to do u substitution to get 2 to the u. Okay, these are just power rules in general. Take the derivative of e to the e. Remembering that e to the e is just a number, the derivative of any number is 0. Derivative of e to the x, this was in the last couple sections. This is just e to the x. C, the derivative of x to the e, that's the same thing as if I had x squared. I would have to follow the same exponent rule because e isn't just a number. So this is e times x to the e minus 1. And on D, we would have to do logarithmic differentiation here. Natural log both sides, which would get our x to the x as x ln x. And then we take the derivative of both sides, the right side being the product rule. Okay, so dy dx is 1 plus ln x, whole thing times x to the x. Okay, thinking about these compound interest formulas, we know these, we've used them. PERT is the one with compounding continuously, and number 1 is for compounding a number of times per year. So we're going to use both of these. Let's start with quarterly. So if we're depositing 2,500, that's our P, times 1 plus the rate as a decimal, divided by the number of times compounded, so quarterly is 5, times 5, or 4, I'm sorry, 4 to the 5, that's a t. And just type that in, and our answer is $3,205.09. B is compounded monthly. So RN is 12. And our total is $3,208.40. And the last one is compounded continuously, and that's the other formula. That's our PERT, which is 2,500 times e to the 0.05 times 5, $3,210.06 is our answer on that one. Okay, if we have a bacterial culture that's growing according to the logistic growth function, y equals 1.25 over 1 plus 0.25 e to the negative 0.4 t, where y is the weight in grams, where t is time in hours. Find the weight of the culture after 0 hours, 1 hour, and 10 hours. What is the limit as t approaches infinity? So A, all we're doing is plugging 0 in for t. Which ends up being approximately 1 gram. B, we're putting in 1 hour for t. Get 1.071 grams. C, we're putting in 10. And we're down to 1.244 grams. And the last one, what is the limit as t approaches infinity? So we're going to look at exponents. This is essentially plugging in infinity. I know that's an interesting concept, but looking at what each term is doing as we approach infinity. So 1.25 on top is just going to go to 1.25. 1 goes to 1. And 0.25 e to the negative 0.4 t, because that's a decay, was going to approach 0 as we approach infinity. So we are going to 1.25 as t approaches infinity. Okay, and that is our section 5.5.